Race conditions is a situation where two or more threads access the same variables or data in a way where the final result stored in the variable depends on how thread access to the variables is scheduled. Race conditions occur when two or more threads read and write the same variables or data concurrently, and the threads access the variables using either of these patterns: check then act, read, modify, write, and where the modified value depends on the previously read value. And the thread access to the variables or data is not atomic. I will explain this in more detail throughout the rest of this video. I will start with an example of the read, modify, write problem, and I have prepared an example, and let me just resize the editor here so you can see what's going on. In this example, I create a single counter here, which is shared by two different runnables. I create two different runnables by calling getRunnable, and as you can see, the counter is passed as parameter to each of them, and here's just a text for printing out some results, and then the threads here are started. One counter, two threads with two runnables sharing the counter, and then the threads start. And what you can see happening inside the runnable here is that each runnable, which then means each thread, will loop for 1 million iterations through this for loop and call this inc and get method here on the counter, and then print out the final value that the counter has counted to. Before I run this example to show you the result, let me just show you the implementation of the counter. As you can see, it has a single private long member variable here, initialized to the value 0. And then you can see the inc and get method here simply increments the count value, the count member variable here, and then returns the value of the count member variable at that time. And as you can see, the get method simply returns the value of the count variable. If we quickly jump back to the example here that runs the counters here, that calls the counters here, then if we have two threads sharing a counter, and each thread counts to 1 million and increments the counter by 1 for each iteration here, or iterates 1 million times here, then that means you have two threads, each iterating 1 million times, which should result in 2 million iterations in total. And thus, when the threads print out the final value down here, at least one of the threads should have counted to the value 2 million, right? That is what we expect. The first thread to finish will of course not have counted to 2 million, because after all, one of the threads will finish before the other. But the second thread we would have expected would have reached 2 million. However, that is not what happens. Let's just run the example here and see what actually comes out. As you can see, the first thread counts to 1 million, and the second thread here has only reached the count of 1.87 million. And let's try to run this again, and you will see different numbers again. There you see they got to the same number, and if we run it again, you see the numbers vary. Now, let me explain to you why that is. To explain that, let's have a look at this diagram that I have here. So what we expect to happen is that the first thread here will read the value of the counter, the value stored inside the counter class here, or the counter object, into a local CPU register where the thread is running, increment the value by 1, and then write that value back to main memory, so that when the second thread here reads the count, it reads the value 1, increments it by 1, and then writes the value 2 back to main memory. However, that is not exactly what happens. Sometimes what might be happening instead of sequential access, as shown here, is interleaved access, which means thread 1 here reads the value 0 from the counter into a CPU register. and then thread 2 at the same time reads the value, or just right after, it doesn't really matter, but it reads the value 0 from the counter as well into a local CPU register for thread 2. Now both threads here increment that value that it has stored in its own CPU register and writes it back. So thread 1 will increment from 0 to 1 and write 1 back. Thread 2 will also increment from 0 to 1 and write 1 back as well. Now 2 threads have actually incremented the counter, and so we expect the value to be 2, but it is actually only 1 because of this interleaved access to the counter here. And this is an example of 2 threads first reading, then modifying and writing back the value here. And the same here, this thread reads, modifies and writes back the value to main memory. And another condition is also fulfilled, which has to be fulfilled. It is that the second value here, the modified value, depends on the previous value, so that the new value count here is the old value plus 1, and it's the same over here, right? If the value had not depended on whatever the old value was, this would have been not a problem, but I will get back to that later on. This section of code here where the problem happens, where the race condition happens, is called a critical section. And it is a critical section because race conditions can occur within this section here, right? As you can see, first we read the value of the count variable here into a local CPU register. This is invisible for you, but this happens underneath the surface inside the Java virtual machine. Then the new value is set as the old value plus 1, so the new value depends on the old value, and then we write it back to count. Again, this looks like one instruction here, but it is actually multiple instructions inside the virtual machine. So this here is a critical section here. The way to fix a critical section is to make the critical section atomic. And by atomic means that only one thread can execute within the critical section at a given time. Once you make a critical section atomic, you get sequential access to the critical section, and then you will force the behavior in the counter that you see here. So first one thread gets access to the count value, reads it into a CPU register, increments it, writes it back, and the second thread then can get access to the count value, the variable's value, read it into a CPU register, increment it, and write it back. In this particular case, one way to solve the problem here, make this critical section atomic, is to simply wrap it in a synchronized block. And that means that only one thread can execute within this block here on the same counter synchronized instance at the same time. And so now you cannot have a situation in which 2 threads read the value of count and then increment that read value. First, whatever thread gets in here will read the value, increment it, and write it back as one atomic operation. Let me just show you how the behavior of this program looks when we are using a counter synchronized instead of a counter. Everything else is pretty much the same thing, right? All the code looks the same. But now increment and get is called by 2 different threads, but the method is now synchronized. All the code in here is wrapped inside of a synchronized block. So as you can see, the first thread finishes a little bit before the second thread, but the second thread now counts to 2 million. And it does that even if we run it again. You can see it's not the same thread that is the last thread. But whatever thread is last always finishes by, with a count to 2 million. Now remember, I told you that it is only if multiple threads are both reading and writing the same variable that race conditions occur. Let me just show you an example where only one thread is writing to the variable, but and only one thread is reading from it. So one thread reads it, one thread writes it. So as you can see here, I have a normal counter here. It's not synchronized, and I have two threads here, and they are being initialized with different runnables. Okay, so the first runnable here, the incrementing runnable, is the one that calls inc and get. So this will cause the inc and get method to be called 1 million times. And then here I have another runnable here which only iterates 5 times, sleeps for 1 millisecond, and then it prints out the value found inside the counter. And as you will see, it's not super visible, but as you will see here, let's try to run this example. As you can see, the thread that counts to 1 million reaches to count that, and then the first time here you can see thread 2 doesn't reads the count value before the first thread has reached 1 million, but then as you can see here, it actually the following times has reached 1 million. And we can try to run it again, and you can see that there is not really any race condition here. And the reason is that in a race condition, the problem here is that the two threads may overwrite each other's updates, or they may not actually see each other's updates, and or the scheduling of the instructions here will cause the two threads to miss each other's updates. And that is not the case here, because there's only one thread making any updates. So the second thread, which is only reading the value, well, it sees all the updates from the other thread. No updates are missed. Well, in theory, it is actually possible, since we're using a non-synchronized counter, it is actually possible that the second thread could miss some values from that were written to the counter, because we have no guarantee about when this value here, this incremented value, is written back to main memory so that it is visible for the thread that reads it. This is known as a visibility problem. So if we want to be absolutely sure, then we would have to declare this variable either volatile, or you would have to access it from within a synchronized block. And I will not get into more detail about all of this. I have covered that in extensive detail in my videos about the Java synchronized keyword, the Java volatile keyword, Java memory model, and the Java happens before guarantee. But just keep in mind that for race conditions to occur, there must be at least two threads which write to the same variable. Otherwise, you do not have a race condition. You may still have a visibility problem, but you do not have a race condition. Let me also just show you a final example here, or another example here, where I start two threads, and each thread is given a runnable, and the runnable gets two counters. And so the runnable will increment the first counter and only print the value of the second counter, right? So you can see here it gets counter A and counter B, and it will increment the first counter here for 1 million times, and then after that it will print out the values of counter A and counter B along with the name of the runnable, and I've called them thread 1 and thread 2. Now you can see that I have switched the counters here so that thread 1 will increment counter 1 and read counter 2, and thread 2 will increment counter 2 and read counter 1. Now in this case we also do not have a race condition, because thread A here, the first thread here, thread 1, is the only thread that is writing to counter 1, and thread 2 is the only thread writing to counter 2. So you do not actually have a race condition, even if you actually have two threads that are accessing these two counters, but the read and write pattern of the two threads is different, and therefore we are not talking about a race condition. let me just try to run this example and see what we get out here. As you can see, as we expected, both thread 1 and 2 reach 1 million here, because we do not have a race condition. They are not overwriting each other's increments, right? Each thread gets to increment one of the counters from 0 to 1 million, and you can see again and again and again. Now, again, because I'm still using the unsynchronized counter here, and inside the counter class, I have not declared this variable here volatile. You could actually, in an application that was long running, you could risk that once in a while one of the increments was not visible until at some later point where the latest value would be synchronized to main memory. So what you might see is a thread reading stale values, but you will never lose an update. Sooner or later the latest correct count value will be written to main memory, and then thread 2 will see it, right? The other thread will see it. You do not lose updates as you do in interleaved access, as I have illustrated here, right? So we also do not have race conditions in this case here. Before I wrap up this video, I want to show you an example of a race condition that is caused by the check then act behavioral pattern. And if you look at the code example here on the left, you can see that I have created here a shared map. It is a concurrent hash map, so this concurrent hash map is capable of having multiple threads access it at the same time without the hash map becoming internally inconsistent. Then I create 2 threads here, each with a runnable, the same runnable actually, and not the same instance, but the same implementation of the runnable interface, and then they get access to the shared map. Then the threads are started. Now let's have a look at what happens down here. Each of the 2 runnables that are created will loop 1 million times, and for each of these 1 million times, it will check if the shared map contains the key. If it does actually contain the key, the map, it will the thread will remove that value from the map. And if that value is null, then it will print out that for iteration I, the value for the key was null. If the map does not contain the key, then the thread will insert that key. And thus, sooner or later, there will be some values inserted into the key, into the map for the given key here. Now, on the surface, it looks like that when we have just checked if the map contains the key, then we cannot then remove the key and then get the value null back, especially not when we never insert a null value into the map. But it is actually still possible when we have 2 threads running this runnable here, this runnable code against the same shared map. And let me just explain to you how that is possible. If both of the threads execute the if statement at the same time, at a time where the map actually contains the key value pair here, so it contains a key with the value key, and the second thread here executes the exact same statement at the same time, then both of these if statements will evaluate to true, and thus the instruction here, map remove key, will be executed in both threads. That is this instruction here. However, the concurrent hash map will not allow both threads to remove the key value pair. Only one of them gets to remove it, and the other one gets a null value back. And that is why once in a while the value might actually be null, because even though we have just determined that the map contains the key, before the thread gets to execute this statement here, the other thread has removed this key here. So in between this instruction and this instruction, the key is removed by the other thread. And thus we can have the situation here where the value is null. Now let's try to run this example and see what we get out. And as you can see, we do get quite a few iterations where the value is null. It's not every iteration, you can see. Sometimes there's a bit of a gap between the threads as well. But sometimes it happens quite a lot, as you can see, but it is not consistent. It is not every single time that the value is null. You can see here, it jumps from 29 to 36 before it reaches this situation again, this thread. The solution to this problem here is, of course, to make the critical section, which is this check here, check then acts, to make this check atomic, and we can do that simply by wrapping it inside of a synchronized block here, and we synchronize on the shared map. It has to be the same object that the two runnables are synchronizing on, otherwise the synchronization will not block the other thread. And the only shared object these two threads have is the shared map here. So now only one thread can execute the check here with the if, remove, else insert, check then act behavior. But since it is not the whole loop that is made synchronized, it means that both threads can still make progress. Both threads can still iterate through the loop, but only one of them at a time can enter into this block here, this critical section, which is now atomic. Now let's run this example again, and we should not get any, you can see now from the output, we never have a situation where a thread first checks that the map contains the key and then afterwards removes a key, removes the key value pair, and the value is null for that key. That no longer happens anymore, because there can no longer be another thread that removes the key in between this instruction and this instruction. That's all for this video about race conditions in Java. Remember to check out the description below the video for links to related videos about topics such as Java Volatile, Java Synchronized, etc., etc. And if you liked the video, hit the like button. And if you want to see more videos like this, subscribe to my channel.